You're about to discover something that might shatter your dreams of interstellar travel, but will ultimately fill you with even greater awe about our place in the cosmos. The truth is, humanity will almost certainly never leave our solar system. Not because we lack imagination or ambition, but because the universe itself has built walls so vast, so insurmountable, that our entire solar system is effectively a cosmic island from which there is no escape. If you're captivated by the reality that Earth is our eternal home, not our prison, then come along on this journey of cosmic discovery. Make sure to subscribe and give this video a thumbs up. As someone just starting to share these profound truths about our universe, your support helps me reach more minds, eager to understand why our cosmic limitations are actually our greatest gift. One quick question: do you think there's another version of you in a parallel universe right now? What might they be doing differently? Comment down below. I will choose the most creative answer. Now let's begin. Right now, the Voyager 1 spacecraft, humanity's most distant ambassador, is racing through interstellar space at 17 kilometers per second. Launched in 1977, it has traveled over 24 billion kilometers from Earth. That's further than any human-made object has ever ventured. Yet after nearly half a century of travel, Voyager 1 has barely left our cosmic neighborhood. It would take another 40,000 years just to come close to the nearest star, Proxima Centauri, and even then, it would merely drift past in the darkness, silent and dead. This is our reality check. The distances between stars aren't just big, they're so incomprehensibly vast that our brains literally cannot grasp them. When you look up at the night sky, those stars appear close together, like diamonds scattered on black velvet just out of reach. But this is the greatest optical illusion in existence. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's 40 trillion kilometers, a number so large it becomes meaningless to our Earth-evolved minds. Let me put this in perspective using the latest data from the European Space Agency's Gaia mission, which has mapped over 1 billion stars in our galaxy with unprecedented precision. If our entire solar system was shrunk down to the size of a quarter, a coin you could hold in your hand, then Proxima Centauri would be another quarter located 200 meters away. That's 2 football fields. And that's just to our nearest stellar neighbor. To reach the center of our galaxy at this scale, you'd have to travel halfway around the actual Earth. But distance is only the beginning of our imprisonment. The real chains that bind us to our solar system are far more fundamental. They're woven into the laws of physics themselves. You see, as Einstein revealed with special relativity, there's a cosmic speed limit, the speed of light, roughly 300,000 kilometers per second. Nothing with mass can ever reach this speed, let alone exceed it. And even if we could somehow travel at light speed, it would still take 4.24 years to reach the nearest star. NASA's Breakthrough Propulsion Physics program, which ran from 1996 to 2002, spent years investigating exotic propulsion concepts, warp drives, wormholes, quantum entanglement engines. The program's director, Mark Millis, concluded that even the most optimistic theoretical proposals would require energy equivalent to the mass energy of Jupiter just to send a small probe to the nearest star. That's more energy than humanity has produced in its entire history, multiplied by billions. The Parker Solar Probe, launched in 2018, is currently the fastest human-made object ever created, reaching speeds of 195 kilometers per second as it dives close to the Sun. That's 0.065% the speed of light. At that incredible velocity, it would still take 6,500 years to reach Proxima Centauri. And that's using gravity assists from the Sun, a trick we can't replicate for interstellar travel. But here's where the story gets even more sobering. Recent observations from the Hubble Space Telescope and the James Webb Space Telescope have revealed that our galaxy is even more hostile to life than we previously thought. The interstellar medium, the space between stars, isn't empty. It's filled with high-energy cosmic rays, particles accelerated to nearly light speed by supernovas and black holes. Any spacecraft traveling at a significant fraction of light speed would be bombarded by these particles, turning them into deadly radiation that would fry any electronics and kill any living crew in seconds. Dr. Philip Lubin at UC Santa Barbara, who's working on laser propulsion systems for interstellar travel, has calculated that even a tiny gram-sized probe, accelerated to 20% light speed, would hit interstellar dust particles with the force of nuclear explosions. Each grain of dust would blast a crater in the spacecraft. Over the course of an interstellar journey, the probe would be completely eroded away like a sandcastle dissolved by waves. The Breakthrough Starshot initiative, funded by billionaire Yuri Milner and endorsed by Stephen Hawking before his death, aims to send tiny light sail probes to Proxima Centauri using powerful Earth-based lasers. Even this ambitious project, with $100 million in funding, only aims to achieve 20% light speed, with probes weighing a few grams. The journey would still take over 20 years, and we'd wait another 4.24 years for the signal to return. That's a quarter-century round trip for a flyby mission with no ability to stop at the destination. But perhaps the most insurmountable barrier isn't technological, it's biological. Human beings evolved for Earth. Our bodies are precisely tuned to this planet's gravity, atmosphere, radiation levels, and day-night cycle. The twin study conducted by NASA, where astronaut Scott Kelly spent a year on the International Space Station while his identical twin Mark stayed on Earth, revealed alarming changes. Scott's DNA expression changed, his cognitive abilities declined, his cardiovascular system deteriorated, and his immune system went haywire. And that was just from 1 year in low Earth orbit, still protected by Earth's magnetic field. Interstellar travel would expose humans to decades or centuries of zero gravity, cosmic radiation, psychological isolation, and countless other hazards we can barely imagine. The European Space Agency's Aurora program has identified over 40 major technological and biological challenges that must be solved before humans could even attempt a journey to Mars, our neighboring planet. Multiply those challenges by thousands for interstellar travel. Dr. John Moore, an anthropologist at the University of Florida, who has studied the sociology of generation ships, calculated that a self-sustaining interstellar colony ship would need a minimum population of 10,000 people to maintain genetic diversity and avoid inbreeding over centuries of travel. The resources required to keep 10,000 people alive for hundreds of years in the hostile void of interstellar space are beyond anything humanity has ever attempted. The Mars One project, which claimed it would establish a human colony on Mars, collapsed into bankruptcy in 2019 despite massive media attention. If we can't even fund a one-way trip to Mars, a planet we can reach in 9 months, how could we possibly organize and fund a journey to another star that would take centuries or millennia? Let's talk about energy, the fundamental currency of the universe and the ultimate reason why leaving our solar system might be forever beyond our reach. Every calculation, every equation, every model we've developed points to the same crushing conclusion. The energy requirements for interstellar travel are so astronomical that they dwarf not just our current capabilities, but possibly our eternal limitations as a species bound by the laws of thermodynamics. Speaking of the cosmic limitations that keep us forever bound to our solar system, have you ever wondered why light has a speed limit? It's not just some arbitrary rule, it's woven into the very fabric of reality itself. I explored this mind-bending question in my video called Why Light Has a Speed Limit, where I reveal how this universal constant shapes everything from time and space to the possibility of existence itself. Check it out after this one to understand the deeper physics behind our cosmic confinement. The link is in the description and on the card above. The Tsiolkovsky rocket equation, first derived in 1903, is the tyrant that rules all space travel. It states that the amount of fuel needed increases exponentially with the desired velocity. To accelerate a spacecraft to just 10% the speed of light and then decelerate at the destination would require a mass ratio of about 10 to the 9th power. That means for every kilogram of payload, you'd need 1 billion kilograms of fuel. The entire Saturn V rocket that took humans to the moon could only achieve 0.004% the speed of light, and that was just to escape Earth's gravity. Dr. Jeffrey Landis at NASA's Glenn Research Center has calculated that using our best current technology, ion drives powered by nuclear reactors, a journey to Proxima Centauri would take 40,000 years and require more plutonium than exists on Earth. Even fusion rockets, which don't yet exist but are theoretically possible, would require tens of thousands of tons of deuterium and tritium for a journey that would still take centuries. Project Daedalus, a study conducted by the British Interplanetary Society from 1973 to 1978, designed an unmanned probe that could reach Barnard's star in 50 years. The design called for a 2-stage fusion rocket weighing 54,000 tons, about the same as a naval aircraft carrier. It would need 30,000 tons of deuterium and 20,000 tons of helium-3 as fuel. Here's the problem. Helium-3 is so rare on Earth that we'd need to mine it from Jupiter's atmosphere, requiring an industrial infrastructure in space that would itself take centuries to build. The more recent Project Icarus, initiated in 2009, attempted to update Daedalus with modern technology. After years of study, the team concluded that even with optimistic assumptions about fusion technology, the energy requirements remain prohibitive. Dr. Richard Obusi, the project leader, stated that we'd need breakthroughs not just in fusion, but in exotic physics that may not even be possible. But let's imagine we solve the fusion problem. Let's say we master controlled fusion and can build rockets with specific impulses 10 times better than anything we have today. We still face the tyranny of time. The latest data from the Kepler Space Telescope and TESS, Transiting Exoplanet Survey satellite, has identified over 5,000 exoplanets, with potentially habitable worlds orbiting stars dozens or hundreds of light years away. Even at 10% light speed, which would require perfect fusion rockets, a journey to a potentially habitable planet like Kepler-4 52b would take over 14,000 years. The human species has only existed for about 300,000 years. Recorded history spans just 5,000 years. The idea that we could maintain a technological civilization capable of supporting an interstellar mission for longer than our entire recorded history is pure fantasy. No human institution has ever lasted more than a few thousand years. The Catholic Church, one of our longest surviving organizations, is only 2,000 years old. How could we possibly maintain the continuity needed for journeys spanning tens of thousands of years? Energy isn't just about propulsion. Life support systems require constant power. The International Space Station, orbiting just 400 kilometers above Earth, requires about 90 kilowatts of power from solar panels the size of a football field. It needs constant resupply missions costing billions of dollars annually. An interstellar spacecraft would need to be completely self-sufficient for centuries, recycling every atom of air, water, and food with perfect efficiency, something we've never achieved even in Earth-based experiments. Biosphere. 2. The ambitious attempt to create a sealed, self-sustaining ecosystem in Arizona failed catastrophically. Despite $200 million in funding and the best ecological science of the 1990s, the 8-person crew couldn't survive 2 years without outside intervention. Oxygen levels plummeted, crops failed, and the ecosystem collapsed. If we can't create a self-sustaining environment on Earth with unlimited solar energy and Earth's gravity, how could we possibly do it in the hostile void of interstellar space? The thermodynamics of interstellar travel are equally unforgiving. The second law of thermodynamics, entropy always increases, means that any closed system will gradually decay into disorder. An interstellar spacecraft is the ultimate closed system, unable to receive supplies or repairs from Earth. Every component would gradually degrade, metal would fatigue, seals would fail, electronics would succumb to cosmic ray damage. The Voyager spacecraft, built with 1970s technology, are already failing after less than 50 years. Most of their instruments are dead, and they'll go completely silent by 2025. Dr. Paul Davies at Arizona State University has calculated that cosmic rays would gradually transmute the hull of any interstellar spacecraft, turning metals into increasingly brittle isotopes. After a few centuries, the hull would be so weakened that it could catastrophically fail from the smallest impact. No material known to science could maintain its integrity over the millennia required for interstellar travel at conventional speeds. But there's an even more fundamental energy problem that few discuss: the energy cost of information. As a spacecraft travels farther from Earth, the energy required to transmit data increases with the square of the distance. Voyager 1, at just 24 billion kilometers from Earth, requires a 70-meter deep space network antenna and 20 kilowatts of transmission power just to receive its faint signals. A spacecraft at Proxima Centauri would be 1,700 times farther away, requiring nearly 3 million times more energy to maintain the same data rate. The New Horizons mission to Pluto, launched in 2006, took 9.5 years to reach its destination and could only transmit data at about 1 kilobit per second from Pluto's distance. From Proxima Centauri, that data rate would drop to less than 1 bit per day without massive improvements in transmission power or receiver sensitivity. The idea of maintaining meaningful communication with an interstellar mission is technologically implausible. Recent studies of the interstellar medium by the Interstellar Boundary Explorer, IBEX, and Voyager spacecraft have revealed another energy challenge. The heliosphere, the bubble of solar wind that protects our solar system from interstellar radiation, ends at about 120 astronomical units from the Sun. Beyond that, cosmic radiation intensifies dramatically. Any interstellar spacecraft would need massive shielding or powerful magnetic fields to protect its crew and electronics, requiring enormous amounts of additional energy. Dr. Eugene Parker, after whom the Parker Solar Probe is named, calculated that generating a magnetic field strong enough to deflect cosmic rays over a journey to Proxima Centauri would require more power than a nuclear power plant produces, running continuously for centuries. The mass of the reactor and fuel would make the spacecraft so heavy that it would need even more fuel to accelerate, creating a vicious cycle that makes the journey impossible. Perhaps the cruelest joke the universe has played on humanity is this: we evolved the intelligence to dream of the stars, but our bodies are forever chained to Earth. Every cell in your body, every strand of your DNA, every biological system that keeps you alive is exquisitely fine-tuned for one specific planet orbiting one specific star. We are not generic life forms that happen to live on Earth. We are Earth, shaped by 3.8 billion years of evolution in this exact environment. And this biological reality might be the most insurmountable barrier to interstellar travel. The latest research from NASA's Human Research Program has revealed just how profoundly space destroys the human body. When astronaut Scott Kelly returned from his year aboard the International Space Station in 2016, scientists found that 7% of his DNA had changed expression and never returned to normal. His telomeres, the protective caps on chromosomes, had lengthened in space, then shortened dramatically upon return, accelerating his cellular aging. His cognitive performance declined measurably, his gut microbiome was devastated, and his immune system became hyperactive, attacking his own body. And this was just from 1 year in low Earth orbit, still partially protected by Earth's magnetic field. Dr. Dorrit Donneville, director of the Translational Research Institute for Space Health, has stated that radiation exposure during a Mars mission would increase cancer risk by up to 20%. For an interstellar journey lasting decades or centuries, the radiation dose would be uniformly fatal. Every astronaut would develop multiple cancers long before reaching another star. The zero-gravity environment of interstellar travel would be equally catastrophic. The latest data from the Japan Aerospace Exploration Agency shows that astronauts lose 1 to 2% of their bone mass every month in space. After a year, they've lost more bone density than a typical elderly person loses in a decade. On an interstellar journey lasting centuries, human bones would literally dissolve. The calcium leached from bones would form kidney stones, while muscles would atrophy despite hours of daily exercise. But here's something even more disturbing that recent studies have revealed. Space fundamentally alters human reproduction. Experiments on the International Space Station have shown that mammalian sperm count drops to near zero in microgravity. Embryonic development is severely impaired. Mice born in space simulations have devastating birth defects. Dr. Joseph Tash at the University of Kansas Medical Center, who studies space reproduction, has concluded that normal human reproduction might be impossible in zero gravity. This means generation ships, the science fiction dream of breeding successive generations during interstellar travel, are likely biologically impossible. Even if we could somehow shield against radiation and solve the gravity problem, the human reproductive system simply doesn't work in space. We would go extinct before reaching our destination. The psychological barriers are equally insurmountable. The Mars 500 experiment conducted by Russia, China, and the European Space Agency from 2010 to 2011 locked 6 volunteers in a simulated spacecraft for 520 days to study the psychological effects of isolation. Despite careful screening and the knowledge that they could leave at any time, the crew experienced severe depression, sleep disorders, and near-violent conflicts. One crew member became so psychologically disturbed that he refused to leave his quarters for months. Dr. Nick Caners, who has studied astronaut psychology for NASA, has identified a phenomenon called Earth Out, profound psychological crisis that occurs when Earth becomes just another point of light in the sky. No human has ever experienced true Earth Out. Even Apollo astronauts could still see Earth as a distinct blue marble. On an interstellar journey, Earth would disappear entirely, potentially triggering psychological breakdown on a massive scale. The human brain itself rebels against interstellar distances. Dr. Peter Sudfeld's studies of sensory deprivation show that humans require environmental stimulation to maintain sanity. The unchanging view of empty space for decades would create a sensory monotony that could drive entire crews insane. Antarctic research stations, despite being on Earth with regular supply drops and communication with home, still experience crew members developing winter over syndrome, a condition marked by depression, anxiety, and cognitive decline. Recent discoveries in microbiome science have added another layer of impossibility. The human body contains trillions of bacteria, viruses, and other microorganisms that are essential for our survival. These microbiomes are constantly refreshed by interaction with Earth's environment. In the sterile environment of a spacecraft isolated for centuries, these microbiomes would inevitably degrade and mutate. Dr. Hernan Lorenzi at the J. Craig Venter Institute has shown that astronauts' microbiomes change dramatically even during short space missions, with potentially dangerous bacteria becoming dominant. The closed environment of an interstellar spacecraft would become a petri dish for microbial evolution. With no new genetic material from Earth, bacteria and viruses would mutate in unpredictable ways. Disease outbreaks would be inevitable and potentially untreatable. The Spanish flu pandemic of 1918 killed 50 million people on Earth, where victims could be isolated and new medical supplies produced. On an interstellar spacecraft, a single pandemic could kill everyone with no possibility of outside help. Genetic degradation presents another insurmountable challenge, Dr. John Moore's anthropological studies show that a minimum population of 10,000 is needed to maintain genetic diversity over centuries. But recent genomic modeling by Dr. Frederick Marin at the University of Strasbourg suggests even larger numbers might be needed. His simulations show that genetic disorders would accumulate over generations, leading to increasing rates of birth defects, mental disabilities, and early death. The concept of genetic bottlenecking becomes terrifying over interstellar timescales. The Toba supervolcanic eruption 74,000 years ago reduced humanity to perhaps 10,000 individuals, creating a genetic bottleneck whose effects we still carry today. An interstellar colony ship would face far worse bottlenecking, trapped in a closed population for millennia. By the time they reach their destination, they might no longer be genetically viable as a species. Food production in space remains an unsolved problem despite decades of research. The vegetable production system on the ISS has successfully grown lettuce and other simple crops, but these experiments require constant resupply of nutrients from Earth. Creating a truly closed-loop food system that could sustain thousands of people for centuries has never been achieved. Every experiment in closed ecological systems on Earth has failed, usually within months. Dr. Raymond Wheeler, who leads NASA's Advanced Food Technology project, has calculated that feeding a crew of just 6 people on a Mars mission would require a greenhouse the size of a football field. For an interstellar mission with thousands of people lasting centuries, you'd need agricultural spaces larger than Manhattan, all of which would need to be accelerated to interstellar speeds, requiring even more impossible amounts of energy. Water recycling presents similar challenges. The ISS recovers about 93% of water from urine and humidity, but that 7% loss would be catastrophic over centuries. There are no water sources in interstellar space. Every atom of water lost through inefficiency or accident would be gone forever. A single system failure could doom the entire mission through dehydration. The latest research on aging has revealed that cosmic radiation doesn't just cause cancer, it accelerates aging at the cellular level. Dr. Frank Cucinotta, former chief scientist for NASA's Space Radiation Program, has shown that cosmic ray exposure causes telomere shortening, mitochondrial damage, and stem cell depletion. Interstellar travelers would age rapidly, experiencing the health problems of 80-year-olds while chronologically in their 40s. There's a chilling possibility that explains why the universe seems so empty, why we've never detected signals from alien civilizations despite billions of potentially habitable planets. Interstellar travel might be impossible for all biological civilizations, not just humanity. This cosmic quarantine, enforced by the laws of physics themselves, could be the great filter that keeps intelligent life confined to single-star systems until they inevitably go extinct. The Fermi paradox, first articulated by physicist Enrico Fermi in 1950, asks a simple but profound question. If the universe is so vast and old, where is everybody? The latest data from the Kepler Space Telescope and TESS has identified over 5,000 exoplanets, with statistical models suggesting our galaxy contains at least 300 million potentially habitable worlds. The James Webb Space Telescope has detected water, methane, and other biosignature gases in the atmospheres of multiple exoplanets. Life should be common. Yet the universe appears silent. Dr. Robin Hansen's Great Filter hypothesis proposes that there's some nearly impossible steps in the evolution from dead matter to interstellar civilization. Most scientists hoped this filter was behind us, perhaps the emergence of life itself or the evolution of complex cells. But what if the filter is ahead of us? What if it's the impossibility of interstellar travel itself? The search for extraterrestrial intelligence, SETI, has been scanning the skies since 1960, using increasingly powerful radio telescopes to listen for artificial signals. The Allen Telescope Array in California monitors millions of star systems simultaneously. The breakthrough. Listen Project, funded with $100 million, uses the world's most powerful telescopes to search for signs of intelligent life. After more than 60 years of searching, we've found nothing but silence. Dr. Anders Sandberg at Oxford's FutureOfHumanity Institute has calculated that if even one civilization in our galaxy had achieved interstellar travel 1 billion years ago and expanded at just 1% the speed of light, they would have colonized the entire galaxy by now. The fact that Earth shows no evidence of past visitation suggests that interstellar colonization has never happened, despite billions of years of opportunity. Recent archaeological and geological studies have found no evidence of ancient alien visitation on Earth. The Silurian hypothesis, proposed by Dr. Gavin Schmidt and Dr. Adam Frank in 2018, examined whether we could detect an industrial civilization that existed on Earth millions of years ago. They concluded that while such evidence would be subtle, certain markers like plastic particles, nuclear fallout, or mass extinctions would be detectable. We find no such evidence, suggesting Earth has never been colonized by interstellar travelers. The infamous Oumuamua object that passed through our solar system in 2017 sparked speculation about alien technology. This interstellar visitor had an unusual elongated shape and unexpected acceleration. Dr. Avi Loeb from Harvard suggested it might be an alien light sail. But follow-up observations and analysis by the European Space Agency concluded it was most likely a natural object, perhaps a fragment of a destroyed planet or a cosmic dust bunny of ultralight material. What Oumuamua did prove is that interstellar objects do pass through our solar system. If alien civilizations were sending out robotic probes, we should have detected them by now. The fact that we haven't suggests they don't exist, supporting the hypothesis that interstellar travel remains impossible even for advanced civilizations. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating extraterrestrial civilizations. Recent updates to the equation using data from exoplanet discoveries suggest there should be between 1,000 and 100 million civilizations in our galaxy. Yet the breakthrough LISTEN project, which can detect radio transmissions from thousands of light-years away, has found nothing. Dr. Milan Ćirković at the Astronomical Observatory of Belgrade has proposed the astrobiological Copernican principle, the idea that Earth and humanity are typical rather than exceptional. If we're typical and will never achieve interstellar travel, then neither will other civilizations. The universe might be full of intelligent life, all trapped in their home systems by the same insurmountable physics that trap us. Recent studies of stellar evolution add another dimension to this cosmic imprisonment. Red dwarf stars, which make up 75% of all stars, seem ideal for life because they burn for trillions of years. But Dr. Manasvi Lingam and Dr. Avi Loeb have shown that planets orbiting red dwarfs face unique challenges: tidal locking, stellar flares, and extreme temperature gradients. Even if life evolves on these worlds, the conditions might make technological civilization impossible. The concept of the galactic habitable zone further constrains possibilities. Too close to the galactic center, and radiation from the supermassive black hole and frequent supernovas would sterilize planets. Too far out, and there aren't enough heavy elements for planet formation. Dr. Guillermo Gonzalez at Ball State University estimates that only 10% of stars in our galaxy are in locations suitable for complex life. Combined with the impossibility of interstellar travel, intelligent civilizations might be isolated islands in a vast cosmic ocean. The recent discovery of phosphine in Venus's atmosphere, initially thought to be a potential biosignature, illustrates another aspect of our cosmic isolation. Even if microbial life exists on Venus, just one planet away, we have no way to confirm it without sending probes. If we can barely explore our immediate planetary neighbors, how can we hope to reach the stars? Dr. Charles Lineweaver at the Australian National University has calculated that Earth-like planets around Sun-like stars formed on average 1.8 billion years before Earth. If interstellar travel were possible, these older civilizations should have already colonized the galaxy multiple times over. The fact that they haven't strongly suggests it's impossible. The zoo hypothesis proposed by Dr. John Ball in 1973 suggests that alien civilizations are deliberately avoiding contact with Earth to allow our natural development. But this requires coordination across potentially millions of civilizations over billions of years, an impossibility given light-speed communication limits. It's far more likely that civilizations simply can't reach each other. Recent advances in our understanding of planetary formation make the isolation even more profound. The ALMA telescope in Chile has observed protoplanetary disks around young stars, showing that planet formation is chaotic and violent. Most planets are ejected from their systems or consumed by their stars. The stable, circular orbits that Earth enjoys are rare. Even if life is common, stable conditions lasting long enough for intelligence to evolve might be exceedingly rare. The discovery of rogue planets, worlds ejected from their star systems and drifting through interstellar space, adds another layer of impossibility. The microlensing observations in Astrophysics survey suggest there might be billions of rogue planets in our galaxy. These frozen, dark worlds could never support life as we know it, yet they outnumber stars. The universe is far more hostile to life than we imagined. Dr. Peter Ward and Dr. Donald Brownlee's rare Earth hypothesis argues that complex life requires an incredibly unlikely combination of factors: a stable star, a large moon to stabilize rotation, a Jupiter-sized planet to deflect asteroids, plate tectonics to regulate climate, and countless other coincidences. When combined with the impossibility of interstellar travel, it suggests that intelligent civilizations are not just isolated, but vanishingly rare. If you want to dive deeper into why Earth might be extraordinarily unique in the cosmos, I highly recommend Ward and Brownlee's book called Rare Earth: Why Complex Life is Uncommon in the Universe. They present compelling scientific evidence that complex life like ours might be so rare that we could be alone, not just in our galaxy, but in the entire observable universe, and much more. The link of the book is in the description. Make sure to check it out. The recent detection of fast radio bursts, FRBs, sparked hope they might be alien signals. These millisecond duration radio pulses release enormous energy and come from distant galaxies. But follow-up observations by the CHIME telescope in Canada have shown their natural phenomena, likely from magnetars, highly magnetized neutron stars. Once again, what seemed like possible evidence of advanced civilizations turned out to be natural. Every few years, a new headline proclaims a breakthrough that will finally make interstellar travel possible. Fusion rockets, antimatter engines, solar sails, Bussard ramjets, Alcubierre warp drives. Each promises to overcome the tyranny of distance and energy. But when you examine the actual physics, when you run the real numbers, when you confront the engineering realities, every single one of these technologies crumbles into impossibility. We're not just lacking the technology for interstellar travel. The laws of physics themselves conspire against us in ways that no amount of technological progress can overcome. Let's start with fusion rockets, often touted as the most realistic option for interstellar travel. The British Interplanetary Society's Project Daedalus, updated by Project Icarus, designed a fusion-powered probe that could theoretically reach 12% of light speed. But here's what the optimistic presentations don't tell you. We've been trying to achieve controlled fusion for over 70 years and still can't make it work on Earth, let alone in space. The ITER fusion reactor in France, under construction since 2007 with a budget exceeding 20 billion euros, won't achieve first plasma until 2025 at the earliest. Even when operational, it will only run for a few minutes at a time and will consume more energy than it produces. The National Ignition Facility at Lawrence Livermore achieved fusion ignition in December 2022, but the total energy input still exceeded the output by a factor of 100 when you account for the entire system. Dr. Robert Bussard's interstellar ramjet concept seemed to solve the fuel problem by scooping up interstellar hydrogen as it travels, but Dr. Daniel Whitmire's analysis showed that the drag from collecting this fuel would exceed the thrust it could provide. The interstellar medium is so sparse, about 1 atom per cubic centimeter, that you'd need a scoop thousands of kilometers wide to collect enough fuel. The engineering required to build and maintain such a structure is pure fantasy. Antimatter propulsion offers the highest theoretical specific impulse, converting matter directly into energy with 100% efficiency. But antimatter is the most expensive substance on Earth. The Large Hadron Collider, humanity's most powerful particle accelerator, produces about 10 nanograms of antimatter per year at a cost of millions of dollars per nanogram. To fuel an interstellar mission would require kilograms of antimatter, more than we could produce in 1 billion years at current rates. Even if we could produce antimatter efficiently, storing it presents insurmountable challenges. Antimatter annihilates on contact with normal matter, releasing enormous energy. The penning traps used to store antiparticles can only hold them for minutes or hours. Dr. Gerald Smith at Pennsylvania State University calculated that the magnetic fields required to store antimatter for an interstellar journey would require more energy than the antimatter itself could provide. Solar sails and laser propulsion seem more feasible because they don't require carrying fuel. The Breakthrough Starshot project proposes using powerful lasers to accelerate tiny probes to 20% light speed. But the engineering challenges are staggering. The laser array would require 100 gigawatts of power, more than the entire electrical output of France. The beam would need to maintain focus over interstellar distances, which is physically impossible due to diffraction. Dr. Philip Lubin, who developed the laser propulsion concept, acknowledges that even a perfectly focused beam would spread to thousands of kilometers wide by the time it reached the distance of Proxima Centauri. The acceleration phase would subject the probes to 60,000 times Earth's gravity, destroying any conceivable electronics. And these are just gram-scale probes with no ability to slow down at the destination. They would zip through the target system in hours, able to collect only the most basic data. The Alcubierre warp drive, based on legitimate solutions to Einstein's field equations, would theoretically allow faster-than-light travel by warping space-time itself. But Dr. Michael Fenning and Dr. Larry Ford showed that it would require exotic matter with negative energy density, something that has never been observed and may not exist. Even if exotic matter exists, Dr. Sergei Krasnikov calculated that creating a warp bubble would require more negative energy than the total positive energy in the observable universe. Recent work by Dr. Alexei Bobrik and Dr. Gianni Martiri claimed to reduce the energy requirements for warp drives, but their solutions still require energy equivalent to the mass of Jupiter and can only work at subluminal speeds, defeating the entire purpose. Every attempt to make warp drives practical runs into fundamental barriers that appear insurmountable. Wormholes, another staple of science fiction, face similar problems. Even if traversable wormholes could exist, which requires exotic matter we've never observed, they would be catastrophically unstable. Dr. Kip Thorne's analysis shows that any attempt to traverse a wormhole would cause it to collapse faster than light could cross it. The quantum effects near wormhole throats would create a firewall of radiation that would incinerate anything attempting passage. The M drive, which claimed to produce thrust without propellant by bouncing microwaves inside a cavity, generated enormous excitement before being definitively debunked. Tests by NASA Eagleworks initially seemed promising, but more careful experiments by the Technical University of Dresden showed the apparent thrust was due to thermal expansion and magnetic interactions with testing equipment. The M drive violated conservation of momentum. If it worked, we could build perpetual motion machines. Ion drives and plasma rockets, while real technologies used on spacecraft like Dawn and Deep Space One, are far too weak for interstellar travel. The most powerful ion drive ever built, the Next C, produces about 236 millinewtons of thrust, less than the weight of a sheet of paper. To accelerate an interstellar spacecraft to even 1% light speed would take millions of years. Dr. Mark Millis, who led NASA's Breakthrough Propulsion Physics program, concluded after years of investigation that no known or theoretical propulsion system can make interstellar travel practical. The energy requirements are not just beyond our current technology, they're beyond what any civilization confined to one star system could ever harness. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, classifies civilizations by their energy consumption. A type-Blashulan civilization harnesses all energy reaching their planet from their star. We're currently at about 0.73 on this scale. A Type 2 civilization harnesses the total energy output of their star. Credible interstellar travel requires Type 2 energy levels, but if you're already harnessing your entire star's output, why leave? Recent observations by the Kepler Space Telescope searched for evidence of Dyson spheres, megastructures that advanced civilizations might build to harness their star's energy. Despite examining over 150,000 stars, no convincing candidates were found. This suggests that either advanced civilizations don't exist, or they never achieved the Type 2 status required for interstellar travel. The computational requirements for interstellar navigation present another impossibility. Dr. Paul Gilster at the Tau Zero Foundation calculated that navigating to another star requires knowing your position and velocity with extraordinary precision. At 20% light speed, a navigation error of just 1 part in a billion would cause you to miss your target star system entirely. The computational power required to process sensor data and make course corrections in real time exceeds what any conceivable computer could provide. Radiation shielding for electronics presents an unsolved problem. Cosmic rays cause single-event upsets in computer memory, corrupting data and crashing systems. The Mars Science Laboratory experienced over 200 memory errors during its 9-month journey to Mars. Over an interstellar journey lasting decades, every computer system would be corrupted beyond recovery. Error-correcting codes can only do so much. Eventually, the hardware itself fails. The recent failure of the Arecibo radio telescope, which collapsed in 2020 after 57 years of operation, illustrates the impossibility of maintaining technology over interstellar timescales. Despite constant maintenance and upgrades, critical cables fatigued and failed. An interstellar spacecraft would need to operate perfectly for centuries with no possibility of repair or replacement parts. Dr. Paul Davies has pointed out that even if we solved all the propulsion and engineering challenges, the software problem might be insurmountable. No human-written code has ever operated reliably for more than a few decades. The Voyager spacecraft require constant software updates from Earth to keep functioning. An interstellar mission would need artificial intelligence capable of rewriting its own code for centuries, a capability we don't have and might never achieve. Even if we could somehow overcome every physical, biological, and technological barrier to interstellar travel, there remains one insurmountable obstacle that dooms our species to eternal confinement: economics. The cost of interstellar travel isn't just expensive, it's so astronomically beyond any possible economic system that it represents more wealth than our entire civilization could accumulate over millions of years. This isn't about lacking political will or proper funding priorities. It's about the fundamental impossibility of marshalling resources on the scale required. Let's start with concrete numbers from real space missions to understand the crushing economic reality. The Apollo program, which put 12 humans on the moon for a total of 80 hours, cost $25 billion in 1973 dollars, approximately $280 billion in today's currency. That's $23 billion per person, delivered to a destination only 384,000 kilometers away. The International Space Station, humanity's most expensive single project, has cost over $150 billion to maintain 6 people in low Earth orbit. Now scale this to interstellar distances. Proxima Centauri is 110 million times farther away than the Moon. Even if we achieved miraculous efficiency improvements of 1,000,000-fold, the cost to send one person to the nearest star would exceed the entire global GDP for thousands of years. Doctor. Philip Lubin's breakthrough starshot, which aims to send gram-sized probes to Proxima Centauri, requires $100 million just for initial research. The full mission would cost tens of billions, and that's for probes weighing less than a paperclip. The economic impossibility becomes clearer when you consider resource requirements. A generation ship carrying 10,000 people, the minimum for genetic diversity according to anthropologist Dr. John Moore, would need to be a self-contained world. The Stanford Torus, a rotating space habitat design from the 1970s, was estimated to cost $1 trillion in today's currency for a population of 10,000. That's just for a station orbiting Earth. An interstellar version would cost thousands of times more. Dr. Alan Bond, who led Project Daedalus, calculated that building their unmanned probe would require more resources than the entire global economy produces in a decade. The probe would need 50,000 tons of deuterium and helium-3, requiring strip mining the Moon or Jupiter's atmosphere. Establishing the infrastructure to extract, process, and transport these fuels would itself require centuries of economic development beyond anything humanity has achieved. The gross world product, the total economic output of our entire civilization is approximately $100 trillion annually. But this number is misleading because most economic activity is service-based, not material production. The total industrial output available for space projects is a tiny fraction. NASA's budget, the world's largest space agency, is only $25 billion, 0.025% of global GDP. Even if the entire world united behind interstellar travel and devoted 10% of global GDP to the project, an impossibility given human needs for food, shelter, healthcare, and defense, it would take millennia to accumulate the necessary resources. Resource depletion presents another economic impossibility. An interstellar spacecraft would require rare elements like hafnium for reactor control rods, beryllium for neutron reflectors, and vast quantities of rare earth elements for electronics. Dr. Robert Zubrin calculated that building a single fusion rocket would consume more of certain rare elements than exists in Earth's accessible crust. We would literally run out of critical materials before completing even one interstellar vessel. The opportunity cost of interstellar travel is staggering. The resources required to attempt an interstellar mission could instead solve every problem on Earth: end poverty, reverse climate change, cure diseases, and create abundance for all humanity. No society would choose interstellar travel over immediate human needs. The political impossibility of convincing billions of people to sacrifice for a mission that would benefit only a few thousand with no return for centuries ensures that funding would never materialize. Historical precedent confirms this economic impossibility. The Ming Dynasty's treasure fleets, which explored the Indian Ocean in the early 1400s, were abandoned because the cost exceeded any possible benefit. The Apollo program, despite its success, was cancelled because the public wouldn't support the expense. If we can't sustain funding for lunar missions, how could we possibly fund something millions of times more expensive? Dr. Seth Shostak from the SETI Institute has pointed out that radio communication is millions of times more cost-effective than physical travel. Sending information at light speed costs essentially nothing compared to sending matter. This economic reality means that any rational civilization would choose to explore the universe through telescopes and radio waves rather than spacecraft. The fact that we see no evidence of either suggests that even advanced civilizations face these same economic constraints. The compound interest problem makes long-term funding impossible. Nobel economist Paul Krugman calculated that investing in Earth-based development always provides better returns than space investment. A dollar invested in Earth technology compounds over time, while a dollar spent on an interstellar mission provides no return for centuries. No rational economic actor, whether individual, corporation, or government, would choose the interstellar investment. Energy economics provides the final nail in the coffin. The total energy consumption of human civilization is about 20 terawatts. Accelerating a 1,000-ton spacecraft to 10% light speed requires about 10 to the 21 joules, equivalent to humanity's total energy production for 15 years. The energy would need to be delivered in space, requiring lifting millions of tons of fuel or building massive space-based infrastructure. The economic cost of this energy alone exceeds the total wealth humanity has accumulated throughout history. Dr. Robin Hansen's analysis of the economics of colonization shows that even if interstellar travel were technically possible, it would never be economically viable. The investment required to establish a colony would never be recouped because the colony would become economically independent long before it could repay the initial investment. No economic system based on return on investment could justify interstellar colonization. The insurance and liability issues alone would make interstellar missions impossible. Who would insure a mission where everyone involved would be dead for centuries before success or failure was known? how could any legal system handle contracts spanning millennia? The Lloyd's of London insurance market, which has operated since 1688, is only 336 years old. No human institution has demonstrated the stability to manage projects lasting longer than recorded history. Recent economic modeling by Dr. Anders Sandberg shows that even post-scarcity economies enabled by advanced automation and artificial intelligence wouldn't change this calculation. The resources required for interstellar travel would always have alternative uses with better returns. A civilization capable of building interstellar spacecraft would have already solved all material wants, removing any economic incentive for expansion. The cryptocurrency bubble of 2017 to 2021, where speculative digital assets reached valuations of $3 trillion before collapsing, illustrates humanity's economic irrationality. If we can't maintain stable funding for basic infrastructure on Earth, the idea that we could sustain multi-generational funding for interstellar projects is pure fantasy. Economic cycles, political changes, and human psychology ensure that long-term projects always fail. Dr. Jeffrey Landis at NASA has calculated that even if we discovered a planet made of pure gold orbiting Proxima Centauri, the cost of retrieving it would exceed its value by factors of millions. There is no conceivable resource in another star system valuable enough to justify the cost of interstellar travel. This economic reality ensures that interstellar travel will never progress beyond paper studies and wishful thinking. The collapse of the Soviet Union, which abandoned its lunar program despite massive investment, shows how even superpowers can't sustain space funding. The superconducting super collider, cancelled in 1993 after spending $2 billion, demonstrates that even much smaller scientific projects can't maintain political support. An interstellar program requiring sustained funding for centuries is politically and economically impossible. After confronting all these impossibilities, the insurmountable distances, the energy requirements that mock our capabilities, the biological barriers that would destroy us, the economic costs that exceed all possible wealth, we arrive at a profound truth that might initially seem depressing, but is actually liberating. Earth is not our cradle, it's our only home, forever. And perhaps that's exactly as it should be. You see, the impossibility of interstellar travel isn't a cosmic cruelty or a failure of human ambition. It's a fundamental feature of a universe that values uniqueness, diversity, and local complexity over homogeneous expansion. Every star system is an island universe developing its own unique expressions of matter, energy, and possibly life. The vast distances between stars aren't walls that imprison us. They're moats that protect the magnificent diversity of cosmic evolution. Dr. Peter Ward at the University of Washington has argued that Earth's biosphere is irreplaceable, not just for us, but in the cosmic sense. The specific sequence of events that led to our planet's particular mix of life forms, from the Great Oxygenation Event 2.4 billion years ago to the asteroid impact that killed the dinosaurs 66 million years ago, can never be replicated. We're not just adapted to Earth, we are Earth's unique expression of cosmic possibility. Recent discoveries from the James Webb Space Telescope have revealed that even planets we once thought might be Earth-like are profoundly alien. TRAPPIST-1e, once hailed as potentially habitable, is tidally locked, bathed in deadly radiation, and has an atmosphere, if any, completely unlike Earth's. Kepler 452b, the Earth's cousin, orbits a star significantly different from our Sun, and receives stellar radiation that would make photosynthesis as we know it impossible. Every exoplanet we study reinforces Earth's cosmic uniqueness. This uniqueness extends to our entire solar system. Jupiter's massive gravity has protected Earth from countless asteroid impacts. Our moon, unusually large for a terrestrial planet, stabilizes Earth's rotation and creates tides that may have been crucial for life's origin. Saturn's rings, Mars's ancient river valleys, Venus's sulfuric acid clouds. Our solar system is a cosmic work of art that took 4.6 billion years to create. Why would we abandon this masterpiece to die in the void between stars? Psychological truth is even more profound. Humans are storytelling animals, and our stories are rooted in place. Every myth, every legend, every meaningful human narrative is connected to specific locations on Earth. The Aboriginal Australians' Dreamtime stories encode 60,000 years of connection to their landscape. Greek myths map meaning onto Mediterranean geography. Even our modern stories, from New York's skyscrapers to Tokyo's neon lights, are inseparable from Earth locations. Dr. Yifu Tuan, the pioneering human geographer, showed that human consciousness itself is shaped by our relationship with place. We don't just live on Earth, Earth lives in us. Our neural pathways are shaped by Earth's gravity, our circadian rhythms by its rotation, our emotions by its seasons. To leave Earth wouldn't be exploration, it would be a fundamental severing of what makes us human. The impossibility of interstellar travel also protects us from our own worst impulses. History shows that human expansion often brings destruction, from the extinction of megafauna wherever humans arrived to the devastation of indigenous cultures by colonial expansion. If we could spread across the galaxy, we might become a plague, homogenizing the cosmos's diversity. Our confinement to Earth forces us to learn sustainability rather than endless expansion. Consider what we've discovered just in our own solar system without leaving Earth. The Hubble Space Telescope has revealed galaxies 13 billion light-years away. Radio telescopes have mapped cosmic structures billions of light-years across. The Event Horizon Telescope has imaged black holes in other galaxies. We've detected gravitational waves from colliding neutron stars, analyzed the atmospheres of exoplanets, and discovered that the universe is expanding at an accelerating rate, all from our prison on Earth. Dr. Martin Rees, the Astronomer Royal, points out that we're in a golden age of cosmic discovery that requires no physical travel. Every year brings revolutionary discoveries about the universe's nature. Dark matter, dark energy, quantum entanglement, the multiverse. We're uncovering the deepest secrets of reality from right here on Earth. Interstellar travel would add nothing to our understanding that we can't achieve through observation. The creative constraint of earthbinding might be exactly what forces humanity to transcend in ways that matter. Instead of spreading our current flaws across the galaxy, we're forced to evolve, to become better, to solve our problems rather than escape them. Climate change, inequality, war, disease, these challenges require us to mature as a species. Interstellar travel would be running away. Staying on Earth forces us to grow up. Virtual reality and digital technology offer a different kind of exploration that might be far more meaningful than physical interstellar travel. We can create infinite worlds, explore impossible geometries, and experience forms of consciousness that biological bodies could never support. The inner space of imagination and creativity is truly infinite, unlike the finite, if vast, physical universe. Why die in the void between stars when we can live forever in digital realms of our own creation? Dr. Nick Bostrom's simulation hypothesis suggests an even more radical possibility. We might already be living in a simulation, and the impossibility of interstellar travel might be a deliberate constraint to save computational resources. If true, trying to leave Earth would be like a video game character trying to leave the map. Not just difficult, but conceptually impossible. Our purpose might be to explore consciousness and meaning within our designated realm, not to spread across a universe that might not even exist as we perceive it. The search for meaning doesn't require interstellar travel. Every human who has ever found purpose, love, transcendence, or enlightenment has done so right here on Earth. The Buddha found enlightenment under a Bodhi tree in India. Einstein discovered relativity in Berlin. Shakespeare wrote his plays in London. The greatest human achievements, art, music, literature, philosophy, science, all emerged from deep engagement with our specific place in the cosmos, not from trying to escape it. Recent studies in positive psychology by Dr. Martin Seligman show that human flourishing comes from connection, meaning, and accomplishment within our immediate environment. The fantasy of interstellar travel might actually be a form of escapism that prevents us from fully engaging with the incredible reality of Earth. We have oceans largely unexplored, ecosystems we barely understand, and human potential we've hardly begun to tap. Why fantasize about dying in interstellar space when we haven't even fully lived on Earth? The indigenous wisdom keepers of various cultures have always known what modern science is rediscovering. We are not separate from Earth, but part of it. The Lakota phrase Mitakuye Oyasing means all my relations, recognizing that we're connected to every living thing on Earth. This isn't primitive thinking, it's profound ecological wisdom that Western science is only beginning to appreciate. Our attempts to leave Earth represent a fundamental misunderstanding of what we are. The latest data from NASA's Earth Observing System, a constellation of satellites monitoring our planet, reveals Earth's staggering uniqueness with ever greater clarity. The interplay between our magnetic field, atmosphere, oceans, and geology creates a self-regulating system of mind-boggling complexity. Dr. James Lovelock's Gaia hypothesis, once dismissed as mysticism, now appears prophetic. Earth isn't just a rock we happen to live on, it's a living system that actively maintains conditions suitable for life. Consider what the Perseverance rover has discovered on Mars, our most Earth-like neighbor. Despite finding evidence of ancient water flows and organic molecules, Mars is a frozen, irradiated wasteland with an atmosphere 100 times thinner than Earth's. The planet's core died billions of years ago, killing its magnetic field and allowing solar wind to strip away its atmosphere. This is the fate of virtually every rocky planet in the universe: death. Earth's continued vitality after 4.6 billion years is a cosmic miracle. The Venus Express mission revealed our other neighbor's fate, a runaway greenhouse effect, creating surface temperatures of 460 degrees Celsius and atmospheric pressure 90 times Earth's. Sulfuric acid rain that evaporates before reaching the ground, a day longer than its year. This is what Earth could have become with slightly different initial conditions. The fact that Earth maintained liquid water and moderate temperatures for billions of years required an almost impossible balance of factors. Dr. Dave Waltham at Royal Holloway University has calculated that Earth's stability required coincidences so unlikely that we might be the only planet in the observable universe with a biosphere lasting long enough for intelligence to evolve. The Moon's size, Earth's distance from the Sun, our planet's mass, the timing of continental formation change any factor by a few percent, and Earth becomes uninhabitable. We haven't found a single exoplanet that matches Earth's extraordinary combination of features. This cosmic perspective transforms how we see our confinement to Earth. We're not trapped in a prison. We've won a lottery so improbable that it may have happened only once in the entire universe. Every breath you take contains molecules that have circulated through countless living beings over billions of years. Every atom in your body except hydrogen was forged in the nuclear furnaces of dying stars. You are not on Earth. You are Earth, temporarily organized into a pattern capable of consciousness and wonder. The recent discovery of the Anthropocene geological epoch, the recognition that human activity has become a geological force, reveals our true relationship with Earth. We're not separate from Earth's systems, but part of them. Our cities are Earth's newest geological formations. Our thoughts and dreams are Earth evolving consciousness. The impossibility of leaving Earth isn't a limitation, it's a recognition that we are Earth and Earth is us. Separation is impossible because it's meaningless. Dr. Lynn Margulis revolutionized biology by showing that complex cells evolved through symbiosis, different organisms merging to become one. This process, called endosymbiosis, means that every cell in your body is a community of formerly independent organisms that learn to live together. This is Earth's deepest lesson. Survival comes not from escape or expansion, but from integration and cooperation. The fantasy of interstellar travel represents an adolescent desire to run away from home. Maturity means recognizing that Earth is not our prison, but our body. The overview effect experienced by astronauts who see Earth from space provides our clearest glimpse of this truth. Every astronaut reports the same revelation. Earth is one living system, heartbreakingly beautiful, and utterly alone in the cosmic dark. Edgar Mitchell, who walked on the moon, described it as instant global consciousness. This perspective shift doesn't make them want to leave Earth. It makes them desperate to protect it. They realize that Earth is not our launching pad to the stars, but our eternal home. Recent advances in our understanding of consciousness suggest an even deeper connection. Dr. Giulio Tononi's integrated information theory proposes that consciousness arises from integrated information processing. Earth's biosphere, with its countless feedback loops and information exchanges, might possess a form of consciousness we can barely imagine. The impossibility of interstellar travel might be Earth's immune system protecting its emerging global consciousness from dissolution. The discovery of quantum entanglement in photosynthesis, navigation in birds, and possibly even human consciousness suggests that life is quantum mechanically entangled with Earth in ways we're only beginning to understand. Dr. Stuart Kaufman's work on the adjacent possible shows that Earth's biosphere explores the space of possible forms with a creativity that makes human technology look primitive. Why would we abandon this cosmic laboratory of consciousness for the sterile void between stars? Climate science has revealed Earth's fragility and resilience in equal measure. The Paleocene-Eocene thermal, maximum 56 million years ago, shows how dramatically climate can change, yet life endured and flourished. The Great Dying, 252 million years ago, killed 90% of species, yet Earth recovered with even greater diversity. Earth has survived asteroid impacts, supervolcanic eruptions, ice ages, and mass extinctions. But it might not survive humanity's attempt to abandon it for the stars. The resources required for serious interstellar travel attempts would devastate Earth's environment. Strip mining the moon for helium-3, building massive orbital infrastructure, launching thousands of rockets. The environmental cost would be catastrophic. We would destroy Earth in our futile attempt to leave it. The impossibility of interstellar travel is Earth's self-defense mechanism, preventing a species intelligent enough to dream of the stars, but not wise enough to cherish its home, from committing cosmic suicide. Dr. Carl Sagan's pale blue dot photograph showing Earth as a tiny speck in a sunbeam from 6 billion kilometers away remains our most profound image. That's here, that's home, that's us. Sagan wrote, "On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." This isn't a limitation, it's a profound truth about the nature of existence. Meaning doesn't come from spreading across the universe, but from deepening our connection to our unique place within it. The future of humanity lies not in the stars, but in becoming truly worthy inhabitants of Earth. Imagine what we could achieve if we redirected the resources and imagination wasted on interstellar travel fantasies toward understanding and nurturing Earth. We could decode the languages of whales and dolphins, achieving interspecies communication more profound than any alien contact. We could restore extinct species through genetic technology, bringing back wonders lost to time. We could create cities that enhance rather than destroy ecosystems, achieving a technological harmony that would be the envy of any hypothetical alien civilization. The impossibility of interstellar travel is not humanity's failure, but our graduation exam. A species that can accept its cosmic limits and find meaning within them is ready for whatever comes next. Perhaps consciousness can transcend physical limits in ways we can't imagine. Perhaps Earth will birth new forms of life that make human intelligence look primitive. Perhaps our purpose is to be Earth's way of understanding itself before returning our atoms to the cycles that created us. These possibilities are far more profound than dying in a metal can between the stars. Take a moment to feel the Earth beneath you. Feel the gravity that holds you, not imprisons you, to this cosmic oasis. Breathe the air that has circulated through dinosaur lungs and primordial seas. You are experiencing the only paradise in the universe, the product of billions of years of cosmic evolution. The stars are beautiful to look at, but they are not destinations. They are reminders of how precious and unique our Earth truly is. We will never leave our solar system, and that's the most beautiful truth in the universe. We are home. We have always been home, and home is all we'll ever need. If you made it this far, make sure to hit subscribe and give a thumbs up. Your support means a lot to me. And if you enjoyed this video, I am sure you will love this other on the left side of the screen. What is the most powerful thing in the universe? In this video, we discover the true scale of cosmic power, from supernovas and black holes to gamma ray bursts, quasars, the unimaginable energy of dark energy, the Big Bang, and much more. See you there.